it's me Chiku from Chiku Study Corner. Today we'll be dealing with the chapter 4 of physics, that is magnetism and matter. So, before we learning about magnetism and matter, this chapter can also be called as the magnetic effect of electric current. We have learned about the magnetic effect of electric current in our previous classes, that is in our class 10 standard. We had a chapter named as magnetic effect of electric current. So, let's see. The word magnetism is highly related to another word which we commonly use and which we commonly play with. What is that? That is a magnet. So, a force around a magnet or experience of a force around a magnet is known as its magnetic field. So, now let's define what is magnetic field. Magnetic field is represented by the letter capital B, and that to denote that magnetic field is a vector quantity. Okay? So, in electrostatics, that is in our first two chapters of physics, we dealt with what? Charges which are static, that is charges at rest was for electrostatic. Okay? So now for us in magnetism, what is that? Charges in motion. What does that do? That produces both electric and magnetic fields. So, let's write the definition for the word magnetic field. So, let's write. That is the force experienced by a force around a moving charge. Let's see the definition. So, magnetic field, that is B, is the space around a conductor carrying current or a magnet in which the magnetic field can be experienced. The magnetic effect can be experienced. Okay? So that is the definition for magnetic field. So let's define it once more. What is that? That is the magnetic field B, represented by B vector, is the space around a current carrying conductor or what? A magnet which has the magnetic effect. Okay? So that is to talk about what is magnetic field. So now let's see some more about this term, magnetic field, magnetism, etc. Next term that we have to learn related to magnetic field and magnetism is magnetic intensity. Let's see what's magnetic intensity. That is, it is the number of magnetic field lines passing normally through a unit area surrounding that point. So, what is the magnetic field intensity? Let's take. This is a point at which we have to take the magnetic field intensity. So, what you will do is you will take a unit area. Okay? You will take a unit area. And over here we have our what? magnetic field lines passing through this. So there are so many field lines. This much number of field lines is the magnetic intensity of this point. There is a condition what you only take unit area around that point. Okay, so that is magnetic field intensity. So before talking about magnetic field intensity, we discussed about what is magnetic field. We have some other terms. It's also called in some other names. So let's see what are the other names. So I hope this definition is also clear. It is the number of magnetic field lines passing normally through a unit area around that point, which has the magnetic field passing through them. So let's see the other few names for the magnetic field. So magnetic field, it's represented by B, and it is also called in other two names also. So the first one that we have to learn is intensity of magnetic field. The second one is the density, the magnetic flux density or magnetic induction. So these are the terms that are different names for what magnetic field. So what are they? They are intensity of magnetic fields, magnetic flux density, and magnetic induction. So these are other names for magnetic field. So to talk about the magnetic field intensity, we said it's a number of field lines passing through it. It is also the force experienced by a unit north pole, because when we always took for in the case of static current, that is electrostatics, what did we say? What's electric field intensity? There was a number of lines passing through unit area, number of electric field lines passing through unit area surrounding that point. Same way, the definition for magnetic field is also what? The force experienced by a unit north pole. So now let's write how do you represent this. It has a representation. So let's write the representation. So I'm just writing the north pole over here, and this is magnetic field intensity. So let's see. What did we learn? Magnetic field intensity is represented as phi. Okay, so phi is equal to integral B dot ds. So we write phi B because that is magnetic flux. Okay, for electric flux, how did we represent it? It is phi E, and this is for electric flux. So no need to learn now, that was what we learned before. So phi B is equal to integral B dot ds. So I told you what magnetic flux is B is a vector quantity, whereas phi B is what? A scalar quantity. So what is the unit for phi? That is Weber. It is WB. Or you can write this Weber as Tesla meter square or Weber per meter square. Tesla meter square or Weber per meter square. Weber per meter square. Okay. So this is what is to talk about magnetic field intensity. Now let's see some of the rules that is required to find out the magnetic field or the magnetic field intensities of various conductors, etc. So let's see. The first one is the right hand thumb rule or the corkscrew rule or the right hand screw rule. Let's see what's that. So, right hand screw rule. It gives the direction of the magnetic field. Okay? That is what our right hand thumb rule gives. So, let's say this is the conductor and this is the direction in which the current is acting upon. So, keep the thumb in the direction of the current and then roll your fingers, that too of your right hand. Okay? I'm just showing this because you find this to be my right hand. So, like this. Okay? So, if this is a current carrying conductor and if this is moving upwards, you will hold it like this. And the field lines would go, the magnetic field lines would go like this. Okay? That is how the right hand screw rule works. So, let's see the definition for right hand screw rule. Let's write. Stretch the thumb of your right hand in the direction of what? Of the flow of current. I, you represent current as I, so in the direction of flow of current. Then what happens? The curled fingers, because you hold it like this and then you curl your fingers. So the curled fingers gives the direction or represent the direction, gives the direction of what? Our magnetic field. Okay? So that is the right hand screw rule. Now we have to learn about the Fleming's left hand rule. We learned about the right hand screw rule. So somewhere we learned about Fleming's left hand rule. Was that in the 10th standard? We learned about this rule holding all of your three fingers perpendicularly to each other. Let's see what that rule is. So, Fleming's left hand rule. Let's see what's that. Before, which all fingers do we use? We use our thumb, our pointer and the middle finger. So let's write the three fingers over here first. The thumb, the middle finger, or let's say the pointer and the middle finger. So this pointer is also called as our forefinger. So I'll just tell you a trick. Forefinger. Okay, let's mention this also over here. So, what will our thumb represent? What will the forefinger represent? What will the middle finger represent? Let's see what's that. Thumb will represent the direction of force. Okay. Now let's see what will our middle finger do. Our middle finger, it will give the direction of what? Motion of charge. Motion of charge. And what will the pointer or the middle finger give? That will give the magnetic force. Okay? So this is what is happening. So when you stretch your three fingers perpendicularly to each other, that is, all these three fingers are in right angles. And you will keep, if either of the quantity is mentioned, usually it is the direction of charge or the direction of force mentioned, or it can be magnetic force also. So you hold it like this. Okay? Perpendicular to each other. If given the direction of force is upwards, what will you do? The thumb would face upwards and then you will stretch your fingers. If magnetic force is given in the upward direction, you will hold it like this. If this is, you will hold it like this. So this is how you calculate the what? Or each of these directions. Direction of force, the direction of magnetic force and the direction of charge. So what is this? This is the direction of charge. What gives the direction of charge? This is the finger that gives the direction of charge. Charge starts with C. Magnetic force starts with M, and direction of force starts with F. So this is the father, mother and child. This goes in this order. Father, mother, child. Father, mother, child. What is the father? That's the force, the direction of force. Mother is the direction of the magnetic field. And what is this child? Is the direction of charge. So this is the Fleming's left hand rule. This is a very useful rule. Why is this? This is applicable, or this is used to find out the direction of various quantities that's mentioned. So let's see the force of a moving charge in a magnetic field. Okay. Force experienced by a charged body. Okay, force experienced by a charged body in a magnetic field. So we'll draw a graph first. The graph is like this. This is our graph. This is the x-axis, this is the y-axis, and this is the z-axis. So this is x, y, and z. We'll mention the force in this direction, the magnetic field in this direction, and our charge is moving like this with a velocity v, making an angle theta. Okay, this is our diagram. So what is this? The force is in this direction, the magnetic field is in this direction. The moving charge, I told you, force on a moving charge. It's a moving charge. Okay, moving charge in a magnetic field. So what happens? This charge is moving in this direction. So this is the charge. It's moving with a velocity v. Okay. So I hope you might have understood the diagram. So now let's see how you equate this equation. The charge over here is considered to be q. The charge is, let's take in a small q. The charge is moving with the velocity v in this direction. So what would be this? You can split this into its components and write it in the same way. So what is this? This is v cos theta and this is v sin theta. Okay. So now let's see that what our force is proportional to some quantities. So let us see what all are the quantities. Force is proportional to the charge. Okay, so charge is q. Force is proportional to the velocity, and also force is proportional to our magnetic field, and force is inversely proportional to what? Or no, it's directly proportional. Sorry, it's directly proportional to what is another quantity I mentioned? That is the theta. Which theta? Sin theta. It's proportional to sin theta. So, what can you infer from this? Let's rub this diagram and then we'll write the equation what we get. From this, what do you see? How can you equate this equation? Can we write this as F is proportional to Q, V, B, sin theta? Can we? Yes. To remove this proportionality symbol, we put a constant K, Q, V, B, sin theta. So, the value of K. So, value of K is equal to 1 and hence is neglected, and we write this equation to be, let's write, F is equal to QVB sin theta. So this is our equation. We found out our equation. This is the equation for force or force experienced by a moving charge in a magnetic field. I hope this is clear. We have some special cases to learn. Let's see what are the special cases. So let's write. Let this equation be there. So cases. Okay. The first case that we have to learn is if theta is equal to what? 0 or 180. What happens? Then F is equal to K what? QVB sin theta. Am I right? What is sin 0? Sin 0 is 0, and therefore what would be? F would be equal to 0. This is our first special case. In the first special case, what did we take? We took theta to be 0 or 180. Now let's take theta to be what? This is the second case that we are going to discuss. So our second case, theta is equal to 90 degree. If theta is equal to 90 degree, then what would be our answer? F would be equal to k QVP sin theta. And then sin theta is 1. So because sin 90 is 1, therefore what our equation becomes? F is equal to QVB, that is the maximum. Okay, did you get that? Now let's take the velocity. This charge is not moving. Over here, the third case that we have to learn is neither with this theta. So let's remove this and let's write over here our V is equal to 0. That is, our charge is at rest. What would happen? There won't be any magnetic force experience. Therefore, F would be equal to 0. Okay. These are the special cases that we have to learn under force on a moving force experienced by moving charge in a magnetic field. Now let's discuss the units of our magnetic field. So let's see what all are the units for magnetic field. So unit of magnetic field, that is, the unit is the SI unit. SI unit is equal to Tesla. It is represented as T. So now let's define 1 Tesla. Let's take, if F is equal to 1 Newton and Q, our charge, is equal to 1 coulomb, and it moves at the velocity of 1 meter per second in angles of 90 degree, what would happen? Then the magnetic field would be equal to 1 Tesla. So how would you define that? That is 1 Newton by 1 coulomb into 1 meter per second. Isn't this? So this is how you define our 1 Tesla. So what is that? If the force is equal to 1 Newton, we said, why did we take this as like this, these conditions alone? Because our equation is F is equal to QVB sin theta. If all these quantities are 1, then it is equal to 1 Tesla. Am I right? So let's see. We have taken Q, the charge is equal to 1. We have taken the force is equal to 1. This is equal to 1. Velocity is equal to 1. And sin theta is equal to 90. So sin 90 is equal to 1, and therefore F is equal to 1 into 1 into 1 into 1, that is equal to 1. Therefore it implies it's 1 Tesla. Okay. So that is how we found out this. Let's write the definition as such for 1 Tesla. So if a question comes to define 1 Tesla, how would you write it? That is what we are going to discuss. So 1 Tesla, it is the magnetic field induction. Magnetic field induction, what was that? Another term for that? That was either we told it as density. What density? Magnetic field density, or we call it as magnetic field. So that is, it is the magnetic field induction of at a point if 1 coulomb of charge moves in a magnetic field with the velocity equal to how much? We discussed before, 1 meter per second, equal to 1 meter per second. So that what happens? It experiences a force of 1 Newton. Okay, so it experiences a force of 1 Newton, and this is the definition for 1 Tesla. What is this definition? So now we have to learn about a law called as Biot-Savart's law. So let's see what's a law, and that is the last topic that we'll be discussing in the introduction to magnetism and matter, and we'll see the rest of the chapter later. So let's see what is that. The name Biot-Savart's law is because of the people who found out the law. Let's see. Biot-Savart law. Explain this law. Let's take a current carrying conductor. This is a current carrying conductor. It's a curved current carrying conductor. In that conductor, we take let's mention the current flowing. So the current flowing through this is I. Okay, the current flowing through this is I. And we take a small element. Okay, the small element is dl, and since this is an element of this conductor, we call this element as what? This portion as current element. So what is this? This is actually dl. Since there is current passing through this, this is mentioned as IDL. That is the current element. Okay, so we took a current element and we take a point. Okay, we will mention the point with another color. So this is our point. The point is taken as, let's take P. The point is mentioned as P. Okay, and there is what? A distance between DL and P. So let's draw the line. So this is our distance between DL and P. What does this do? This P would have what? A magnetic field in the, I'm just rubbing this. So this is the direction of dB, that is the magnetic field at the point P. That is what we have to find out. That is the conclusion that we get, the relation between dB from Biot-Savart's law. Okay, so now we know dB, or the point P and DL is in a distance. That distance is R, and the angle between them is theta. Angle between DL and R is theta. Okay, so now let's define this equation. So let's see. I told you we are talking about dB. So dB is what? It is proportional to the first quantity that we mentioned was I, and then we talked about dB is proportional to what? We told about I, then we told about DL, then we told about the point P, what? R dB. So dB is proportional to DL. And then what else is closer? This is our theta. So dB is proportional to sine theta. Okay, and also dB is inversely proportional to 1 by r square. So what all did we discuss? dB is proportional to the current flowing through it. dB is proportional to the dl, the current element. We said, see, IDL, what was that? IDL is the current element. Am I right? The current element. Okay, that is proportional to I, it's proportional to D, it is proportional to the sine theta, the theta angle, that's the angle between R and DL. Sine theta, and it's inversely proportional to the distance between DL and the point P. Okay, inversely proportional to the square of the distance between DL and P. So now let's write the equation. So the equation would be, I'm just rubbing this diagram. So the equation is what? dB is proportional to I dl sine theta divided by r square. Am I right? You just put all these things together in a single line. So this is the equation. So in the previous session, on the previous equation, that is QVB is equal to what? B. In that we had a constant K, and the value of K was 1. But over here, let's see. dB is equal to K I dl sine theta divided by r square. Over here, K is not equal to 1. It has another value. So let's write the value of what? K. So K is written as mu 0 mu r divided by 4 pi, where the value of mu 0 is equal to what? 4 pi into 10 raised to minus 7. So mu r, we don't usually write mu r because the cases that we take are always in vacuum. So what we write is mu 0 by 4 pi is equal to K, and therefore what would be the value of K if this is in vacuum, what would be the value? The value would be 10 raised to minus 7. And this is always dependent on the value. Okay. So this is the 10 raised to minus 7 is the value for K. So this is the equation for Biot-Savart's law. Now let's see how you make it in the vector form. So the vector form of Biot-Savart's law is what we are going to discuss next. So let's see what's the vector form of Biot-Savart's law. And by the way, the direction of dB is given by right hand screw rule or the right hand thumb rule. So let's write it, the vector form. Therefore, dB in vector form is with an arrow is equal to what was our equation? Mu 0 by 4 pi into IDL sine theta divided by r square into r cap. Am I right? Now it's in a vector form. Now let's resolve this and solve this and make it in the simplest form of the equation. So dB is equal to mu 0 mu r. I'm just writing mu 0 mu r divided by 4 pi into I what dl cross r. Okay, we wrote dl cross r. So sine theta, we removed this theta and made it into dl in cross products. So dl cross r, and what would happen? It will be divided by r square. Am I right? And there is an r cap also. Don't forget to mention the r cap. I'm sorry, you don't have to mention the r cap because this is already converted into the cross product. So now let's write. To make this into the vector form, dB is equal to what? You know r cap. The value of r cap over here, what would you give the value of r cap? R cap is equal to r vector divided by r. Let's substitute it over here. So what would happen? Let's write into r cap. So the value of r cap, we know, we'll write the value of r cap over here. R cap is equal to r vector divided by r. So let's substitute this over here. So dB is equal to mu 0 mu r divided by 4 pi into I dl into r. What happens? This is mentioned as r vector divided by r square into r. What is this? This is, we'll write this equation over here. I'm just rubbing this and I'm writing the equation. That is dB is equal to mu 0 mu r divided by 4 pi into I dl r into r. What is this? Can we just derive this over here? So what is this equation given? R into r cap. So this is what would be the answer. R into r cap would give. So the equation dB is equal to mu 0 by 4 pi I dl sine theta into r cap divided by r square. Wasn't this our equation? Let's write this equation in another form. dB is equal to mu 0 by 4 pi into I dl sine theta into r vector divided by what? R cube. Why is that? Because r cap is equal to r vector divided by r. So when you substitute it, you get the equation to be like this. And then dB is equal to what? Mu 0 divided by 4 pi into I dl in bracket in cross r cap divided by r cube. This is our equation. That is what we get. Now what we have to do is, this is what dB. Now we have to find out the integral. So integral dB is what we are going to find. So integral dB is equal to what? That is equal to integral mu 0 divided by 4 pi into I dl sine theta divided by r square. Am I right? Isn't mu 0 by 4 pi a constant? Let's take that out. Okay? So, we'll write the constant b. Integral dB is b. b is equal to what? Mu 0. So, integral dB is b. So, b is equal to integral mu 0 by 4 pi I dl sine theta divided by r square. This is the final equation. So friends, that is all for today's session. I hope you might have understood it and liked it. If you have understood it and liked it, please give my video a huge thumbs up and also subscribe to my channel if you are new to it. And share my videos with your other friends. So see you on the next part of this chapter. Till then, bye-bye.